Hello everyone, welcome to another video. Today I want to talk about variance. Now, we understand variance is a measure of dispersion and it quantifies how dispersed the data is in a distribution. But let's try to understand this in a very specific context how this is more important than other measures of dispersion, such as the standard deviation. While they both talk about dispersion, how could variance be more important in certain specific cases? Let's try and understand that. So I've got this setup right here where I'm looking at a single dice and its distribution, right? So this is a uniform distribution. These are the dice values. They all appear once. So we could say this is a uniform distribution. But when we look at the sum of two dice rolls here, first, let's have a look at the matrix on the right hand side. This is the first dice values. This is the second dice values, and together this forms these 36 values are in fact the sum of dice 1 and dice 2. Notice 7 seems to appear the most number of times, and this is also evident from the distribution of this, right? So this plot is simply telling us which value appears how many times, right? And this is looking like a normal distribution. Well, what we are really trying to answer here now is whether or not the individual standard deviations of the dice, their sum, their addition together is equivalent to the standard deviation of their sum, right? So this is something that we want to see. Turns out the standard deviation for the first dice is 1.7, and these are fair dice. They are identical. So the standard deviation of the second dice is also 1.7. Together, this forms 3.4. It does not equal 2.4, right? So the standard deviation of sum of two dices does not equal the sum of individual standard deviations. So this is false for this specific case, right? So what interestingly, it is true in the case of variance, which is what makes variance very important in many aspects. Because notice now the variance of the sum of two dices equals the sum of individual variances of these dices, right? So 2.9 plus 2.9 in fact equals 5.8. This is super important in many aspects because we could now use variance as a tool to understand perhaps distributions or dispersion in distributions that have more than two dice without having to compute this matrix. Realize that to get this number 5.8, I've had to construct this matrix, of course, and then see the possible values that would appear and then compute variance for that, right? This is how I would get 5.8. But if there were more than two dice, for example, 3, 4, and 5, this would be computationally intensive, right? But this relationship enables me to get to that result by simply adding the individual variances. Think of it in this context, in this way. So consider I have 16 dice now, and to see the possible combinations of all 16 dices, sum of all 16 dices would be too cumbersome. So it would not be a straightforward procedure. I would have to see all those combinations and then compute their variance. But this relationship now allows me to just simply find variance of one dice and add it 16 times. I already know variance of one die, it's 2.9, so I can add it 16 times to see what the variance of combined sum of all 16 dices would exactly be. So this is why variance is more important, and this is true for variance, but it's false for standard deviation. And variance can then help us understand complex distributions by using a very simple relationship.